Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Tifr, Jest, IIT-Jam exam, and other exams related to physical science. And in this lecture, I'm going to solve 2019 CSIR Net Physical Science PYQs. Okay, this is the uh, third lecture of the series. Okay, and before starting the class, I would request the people who haven't subscribed my channel yet, please subscribe my channel. Okay, so I'm going to start now. This is the third lecture of the series. Okay, so we are solving June 2019 CSIR Net Physical Science PYQs. Okay, after we'll solve all the PYQs of 2019 which were asked in June, then December 2019 PYQs, then 2021, 22, 23. So we are going to solve all years papers. Okay. Well, so I'm going to start now. The question number 1. Let me just check the voice. Am I audible or not? All the PYQs. Yes, I'm audible. Okay. So question 1 is the infinite square well potential the infinite square well potential of a particle in a box of size A in a box of size A as shown in the figure as shown in the figure below. assume assume delta less equal to A. Okay, the energy of the ground state compared to the ground state energy the ground state energy before the perturbation was added. Before the perturbation is added. Okay, and options are, option number A is increases by a term of order epsilon. increases by a term of term of order epsilon Option B is decreases by a term of decreases by a term of order epsilon and option number C is increases by a term of order epsilon square. Increases by a term of order epsilon square. Increases by a term of order epsilon square, and option D is, I will make a figure, then it will be the question will be more clearer to you. Okay, option D is decreases by a term of order epsilon square. Okay, so the question is the infinite square well potential of a particle in a box of size A shown in the figure. I'm going to make a figure, okay, below, and assume delta less than equal to A, the energy of ground state compared to the ground state energy before the perturbation is added. Okay, so first I'll make a figure, then it will be clear. Okay, so initially before perturbation, this is the state, okay, of the particle in the box. This is 0 or this is A. Okay, this width of the box is A before perturbation. Okay, and this is particle in infinite one-dimensional box. Okay, now after perturbation, this is like this. Okay, figure is given like this one. Okay. Minus epsilon, this is epsilon, this is delta, and this is delta. Okay, the width of is A. Okay, this is A, and this is like infinite. Okay, this is the figure in the question given. Okay, so this one, right? So the question is, I'll read it again. So the infinite square well potential of a particle in a box of size A shown in the figure below. So this is the shown. Okay, this is the given the figure in the question. Okay, this one. Okay, and the energy of ground state you need to find out compared to the ground state energy before the perturbation is added. Okay, this is the state after perturbation is added. Okay, this is the state when perturbation is not added. Okay, the energy before perturbation is not added. Okay, this is the simple one. Then so this is the figure which is given. Okay, so in this condition we need to find out the ground state energy, and then we need to compare that ground state energy before perturbation. Okay, the ground state energy before perturbation. Okay, so this is the question. Okay, I'll solve it now. I think we have done some mistake here in question. Forward infinite square potential in the box of size A shown in the figure below. Size A is modified as shown in the figure below. Okay, so this is modified. Okay, we have missed this term. Okay, so the infinite square well potential of a particle in a box of size A is modified shown in the figure. Okay, size A modified as shown in the figure. Okay, modified as shown in the figure. Okay, as shown in the figure. So this is the question. Infinite square well potential of a particle in a box of size A is modified as shown in the figure. So this is the modification. Okay, then we need to compare the ground state energy. So we need to find out the ground state energy after perturbation. Okay, and then we need to compare it. Okay, so I'm going and before perturbation, this is the state of the particle. Okay, this is the width of the box A. This one. Okay, A. This is 0. Okay, so the we can see if we see this modification, right, from the center of this box, we will find it this modification is asymmetric. Okay, it is not symmetric. So the perturbation is antisymmetric about center at the box. Okay, since the perturbation is antisymmetric, right, about the center of the box. Okay, the perturbation the perturbation the perturbation is antisymmetric. Perturbation is antisymmetric perturbation is antisymmetric about center at the box. About center about center at the box. So clearly seen, right? This is the center of the box. About the center of the box, the perturbation is antisymmetric. Okay, so if because it's antisymmetric, so there's a condition. If perturbation is antisymmetric about the center of the box, in that case E11, the first order correction in ground state energy. Okay, E11 is becomes 0. Okay, very important one. Okay, this one. So the ground state energy, the first order correction in ground state energy is 0 if perturbation is antisymmetric. Okay, about the center at box. So this is very important. Next, now we will find out. So we will find out E12. Okay, second order correction in ground state energy. Okay, so this perturbation is applied. So this we know, sigma m not equal to 1 mod square of phi 1 phi m, that is mod square upon ground state energy my E1 minus EM naught. Okay, E1 naught minus EM naught. Okay, this is the one. Okay, so this is the formula for second order correction in ground state energy. Okay, here we have made some mistake at perturbation part. So this is W, this is perturbation. Okay, phi m mod square of phi 1 W phi m. Okay, upon E1 naught minus EM naught. Okay, from here we can see E1 naught is greater than EM naught. Okay, E1 naught greater than EM naught. Okay, okay, and also since E11 is 0, this implies E12, the second order correction, is going to be less than 0. Okay, less than 0. So from this we can so this is the one, right? This is the perturbation, right? This is sigma and this is sigma. These are equal in size, guys. Okay, so from there it's clear that so after perturbation, right, the energy of ground state compared to the ground state energy before the perturbation added, if we compare, so we will find that the energy after perturbation energy decreases by a term of epsilon square. Okay, so option D is the correct answer, guys. Okay, option D is the correct answer. Okay, so very simple question. Okay, so this is the one. Okay, so question is to the energy of the ground state compared to the ground state energy before the perturbation is added. Okay, so the energy decreases after perturbation, energy decreases by a term of order epsilon square. Okay, and also very important point is this this perturbation is antisymmetric about the center of the box. Okay, so this question is done. Now next question we are going to solve. Next question, question number 2. Question number 2 is this is also very good question. A quantum particle of mass m, a quantum particle of mass m, quantum particle of mass m in one dimension, confined to a rigid box as shown in the figure, is in its ground state, and infinitesimally an infinite simile thin wall is very slowly is very slowly raised to infinity at the center of the box at the center of the box in such a way that the system remains in its ground state. The system remains in its ground state at all times. Assuming that no energy is lost in raising the wall the work done on the system when wall is fully raised when wall is fully raised eventually separating the original box separating the original box into two compartments into two compartments is okay, and figure is given. I'll make this figure minus L plus L O infinite okay. This is minus L plus L. This is O. Okay, this is the thin wall. And options are 3 pi square h square, 3 pi square h square upon 8 ml square, 8 ml square. Option B is pi square h square, pi square h square upon 8 ml square, 8 ml square. Option C is pi square h square, pi square h square upon 2 ml square, 2 ml square, and option D is 0. Okay, so this is the question. So I'll read it for you. So a quantum particle of mass m is one dimension. Okay, so particle is in one dimension, confined to a rigid box as shown in the figure. Okay, this figure. Okay, now is in its ground state. Okay, the particle is in its ground state, and infinitesimally thin wall. It's very small. Okay, infinitesimally thin wall. Okay, very small thin wall is very slowly raised. Okay, so we have raised the wall very slowly, thin wall. Okay, raised to infinity, like this. Okay, this is infinity, this is infinity, and this is infinity, to infinity. Okay, at the center of the box, from the center of the box, right, at the center of the box we have raised the wall, very thin wall. Okay. In such a way that the system remains in its ground state at all times. Okay, and the condition is system will always remain in its ground state. Okay, we have increased the wall to infinity in such a way that particle will always remain in ground state. Okay. And next, assuming that no energy is lost in raising the wall, and we assume that there is no energy loss. Okay, while raising the wall, the work done, we need to find out the work done on the system when wall is fully raised. Okay, eventually separating the original box into two compartments. Okay, so now we need to find out work done. The wall is completely raised to infinity, right, and it is separating the box into two parts. Okay, two equal compartments. Okay, so we need to find the work done. Okay, so very good question. So I will solve it for you now. Okay, yeah, initially, okay, initial particle in ground state. Okay, initially particle in ground state, initially particle in ground state. So the initial energy is going to be EI. So this condition, right, in this condition, because in this time this wall is not raised, so particle is in ground state, and we know we know the energy, how to get energy of this this system, right, because this is the asymmetric potential well, right, sorry, yeah, symmetric potential well, my apology. So this is going to be we know pi square h cut square. Okay, so it's 1D box, so n equal to n is going to be 1, right? So I will write it n square pi square upon 2ma square, that we know, right? So it is going to be here n square is 1 into pi square h cut square, okay, upon 2 ma square is the width of the wall, right? So this is 2l here, okay, 2l. So it is going to be 2l square, okay. So it is going to be pi square h cut square upon 8 ml square, right? So this is the initial initial energy, okay, when wall is not raised, okay. Next, now wall is introduced. Slowly the particle will in ground state at the wall with width, right? So now wall is introduced. Now wall is raised slowly, okay. If wall is raised slowly, in that case, right, and but there is a condition that uh, particle will remain in ground state, okay. Okay, so now what happened is wall is already raised to infinity and there are two parts, right? But ground state of particle is going to be same, that remains same, right? So in that case, EF is going to be after raising the wall, okay, after raising the wall, after raising the wall, energy EF is going to be here you can see this wall is divided into two parts, okay, two equal parts of length L, okay, but energy of the particle is remaining same. So but length, that width of wall will change, right? So in that case the energy is going to be pi square h cut square, this, and energy we know, right? This one will write n square upon 2ma square, right? 1 into pi square h cut square upon 2m. A is L here only because now length is L. Length will remain L, okay, because it is divided into two parts, two equal parts. So it is going to be pi square h cut square upon 2 ml square, right? So it is F. Now work done we know, right? Work done delta W, okay. Work done is going to be E final minus E initial, right? So it is going to be delta E is going to be E final. E final is this one, pi square h cut square upon 2 ml square, pi square h cut square upon 2 ml square minus pi square h cut square upon 8 ml square, okay, 8 ml square. So we'll solve it. So the work done, this is work done, okay. Work done is going to be 3 pi square h cut square upon 8 ml square, right? 8 ml square, yeah. So this is the answer. Which option is matching? Option number A is the correct one, okay. Option number A, yeah. 3 pi square h cut square upon 8 ml square, okay. Very good question, guys. I hope you understood it. So very simple. Particle will remain in the ground state, but box will separate, get divided into two equal parts, okay. And then each the width of each wall is going to be L instead of 2L in this case, okay. So that's why here the energy is going to be like this, and the width is going to be only L, right? So this one. and the work done we know that E final minus E initial. Right? So this is the one. Very good question, guys. You need to practice questions and revise questions. Okay. Next question we are going to solve. This is question number 2. Now question number 3rd. Question number 3rd is, these are questions which were asked in 2009, June 2019, CSIR NET Physical Science. Okay. Okay. So next question is question number 3rd. The wave function of a free particle. The wave function of a free particle of mass m, of a free particle of mass m, constrained to move in the interval minus L x is between minus L to plus L. In the interval, this is psi equal to psi, which is function of x, okay, equal to a L plus x into L minus x. Okay, this is the wave function of free particle which is constrained to move in interval x is between minus L to L, in interval minus L to L. Okay, where A is the normalization constant, where A is the normalization constant, the probability that the particle will be found to have energy pi square h cut square upon 2 ml square is, okay, is, options are option number A 0, option number B 1 upon root 2, option C 1 upon 2 root 3, and option D 1 upon 5. Okay, so the question is the wave function of free particle of mass m is given. Okay, and which the particle is constrained to move in the interval minus L to plus L. Okay, and wave function is psi equal to A L plus x L minus x, where A is the normalization constant. Okay, now you need to find the probability that the particle will be found to have energy, yeah, pi square h square upon 2 ml square. So you need to find out the probability, okay, whose energy is, when an energy of particle is pi square upon h square pi square h square upon 2 ml square. Okay, very good question. Okay, so I will solve it for you. Okay, first we'll find the energy. Energy of particle, that is En. Okay, it is going to be n square pi square h square upon 2 ma square, right? And here you can see particle is between minus L to L, right? So in that case, the energy is going to be En is going to be n square pi square h square upon 2m. Width is 2L, right? Because L to L, right? Minus L to L. So this is going to be n square pi square h square upon 8 ml square. Okay, so this is the energy eigenvalue. Okay, En we have found. So now we will find E1. Okay, ground state energy E1. For E1, for ground state energy n equal to 1, right? So this is going to be n equal to 1. So E1 is going to be pi square h square upon 8 ml square. Okay, and the wave function of it is going to be phi 1. The wave function is going to be, okay, wave function is going to be width is 2L, right? So this is going to be root 2 upon 2L cos n equal to 1, right? So this is going to cos pi x upon 2L. Okay, this is the wave function. Similarly, E2 is going to be for E2 n equal to 2, right? 2 to the 4. So this is going to be 4 pi square h square upon 8 ml square. Will simplify it, so it is going to be 4 will cancel with 8 by 2, right? This is going to be pi square h square upon ml square. Okay, pi square h square upon ml square. Two ml square. This is 2 times it will get cancelled. 2 ml square. And the wave function phi 2 is going to be root 2 upon 12. N is 2, right here. So it is going to be sine because symmetric potential, right? Sine 2 pi x upon 12. Okay, this is the wave function. And what is the question? Question is we need to find out the probability of the particle. Okay, when its energy is pi square h square upon 2 ml square. Okay, so here we can see for E2 the energy is this pi square h square upon 2 ml square and pi square h square upon 2 ml square. For this energy we have to find the particle, we have to find the probability of particle, finding particle whose energy is this, when energy of particle is this, right? So the energy of particle is this one, right? Pi square h square. So for n equal to 2, that is the energy of particle, that is E2, right, is this. Okay, so we'll find out the probability of finding particle when its energy is E2, right? E2 is this one, pi square h square upon 2 ml square, this one. Okay, for this we need to find out probability. P equal to, we know that is going to be probability, we know, right? If it is not normalized, so we know that is phi 2 psi 1 mod square upon psi psi. Okay, for particle, for probability of finding particle when its energy is pi square h square upon 2 ml square. Okay, so this one phi 2 we know, phi 2 is this, and psi is given, right? Psi is this, psi equal to a l plus this one. Okay, since psi is a sine L plus x, sorry, a sine a L plus x L minus x, this one, L plus x L minus x. Okay, so a L plus x into L minus x. Okay, L minus x. So now we'll calculate it. So PE2 is going to be, this is going to be mod integration minus L2, because this is the limit, right? Minus L2 plus L, okay, plus L, then this one, right? So this is phi 2 phi 1, phi 2 psi, it is just phi. Okay, L is going to be root 2 upon 2L, phi 2 is right, it is sine 2 pi x upon 2L, this wave function, sine 2 pi x upon 2L into a L plus x L minus x, right? You know how to do it, and then dx and mod square upon, this is going to be integration minus L to L. Okay, so this is going to be a square L plus x whole square and L minus x whole square, right? Because psi value is this, right? And now we'll solve it. So this is going to be P into, is going to be, this value is going to be so here we can see, we'll take this a and a will get cancelled and 2L 2 will get cancelled, right? L will take common, 1 upon L, 1 upon root L, right? Then we can see that sine 2 pi x upon 2L, right, into a L plus x L minus x, right? So we'll take this one, 2 gets cancelled, 1 upon L mod integration minus L2 plus L, and this is going to be sine 2 will get cancelled, right? Sine pi x upon L into a will come here, right? A upon L. So this is L plus x L minus x upon this term minus L2 plus L a square L plus x whole square L minus x whole square. So here you can see that this is sine pi x, sine pi x upon L into L plus x into L minus x. This is the odd function, okay, and the limit is between minus L to L. So this is going to be 0, right? If function is odd and then and it is between minus a to a or minus L to L, the integration of this becomes 0, right? We know. So since we can write, since sine pi x upon L sine pi x upon L into L plus x and L minus x is odd function, right? So this means this complete this integration, that is PE2 is going to be 0, or P, probability of finding particle when its energy is pi square h cat square upon 2 ml square, right, is 0. Okay, so which option is matching? Let's see, this is the answer. We'll check which option is matching. Option number A is matching. Okay, so this is the correct answer, guys. Okay, next question. Next question is question number 4. Question number 4 is, it's a good question, guys. Okay, a particle moving in central potential a particle moving in particle a particle moving in a central potential moving in a central potential a particle moving in a central potential is described by a wave function psi r equal to z fr, okay, where r equal to x to y, which is function of x, y, z, is a position vector, is the position vector, is the position vector of the particle, position vector of the particle. The value of L square, must be option A is 2 h cat square, option B is h cat square, option C is 4 h cat square, and option D is 3 by 4 h cat square. Okay, well, so this is a particle is moving in a central potential. Okay, particle is moving in a central potential. Okay, particle is in the influence of central potential, is described by wave function, and a wave function is given. Okay, and r is the position vector which is given, and the okay, position vector of the particle. The value of L square must be, okay, here I think we have missed something. This is position vector of the particle, and fr is the function of, yeah, this is also given, yeah, fr is function of r. Okay, fr is function of r, yeah, fr is function of r. Okay, that is mod r. Okay, Okay, this is also given, and L is the total angular momentum of the particle. Okay, so value of L square we need to find out. Okay, L is the total angular momentum of particle. Okay, so L square is the square of total angular momentum of particle. Okay, so so now we have to solve it. So we have been given, since psi r is given, right? Psi r is given, that is Z Fr. So the central potential, the value of that is, we know, r cos theta, right? Since, so it means psi r is going to be r cos theta into Fr. Okay, and then psi r is going to be, psi function of r is going to be P1 cos theta P1 cos theta RFR. Okay, since we know value of cos theta is equal to P1 in legendary polynomial P1 cos theta. Okay, P1 cos theta, and this implies value of L equal to 1. Okay, so now we know the value of L square we need to find out, right? So we have to find the value of L square, must be, right? The value of L square we know, that is L into L plus 1 into h cut square, right? And from here, because cos theta is P1 cos theta, right? And this implies L equal to 1. Okay, so this means L square is going to be 1 into 1 plus 1 h cut square, and this is going to be 2 h cut square. Okay, this is the answer. Which option is matching? Very simple question. Option number A is matching. Let me check. Option number A is matching. Yeah, that's correct. Okay, so this is the question number 4. Now question number 5 we are going to solve. Okay, question number 5. Question number 5 is, it is also a good question, and this question is from electrodynamics. Okay, consider a plain wire. Consider a planar wire. A planar wire. Consider a planar wire loop as an n-sided regular polygon. N-sided regular polygon consider a planar wire loop as n-sided regular polygon. Okay, n-sided regular polygon in which r is the distance. R is the distance. R is the distance from the from the center to vertex. From the center to vertex. If a steady current I flows through wire. If steady current I flows through the wire. Flows through the wire. The magnitude of magnetic field. The magnitude of the magnetic field magnitude of magnetic field at the center of loop is, at the center of loop is. Okay, options are mu 0 I upon 2r sine 2 pi upon n. Option B is mu 0 ni upon 4 pi r sine pi upon n. Option C is mu 0 ni upon 2 pi r 10 2 pi upon n. And option D is mu 0 ni mu 0 ni mu 0 ni upon 2 pi r 10 2 pi upon n. Okay, sorry, mu 0 ni upon 2 pi r 10 pi upon n. Okay, okay. So the question is, consider a planar wire loop, okay, as an n-sided regular polygon. So you need to consider a planar wire loop as a n-sided polygon, okay, in which r is the distance from the center to vertex. Okay, so r is the distance from center of polygon to vertex, okay, of the polygon. If steady current I flows through the wire, okay, so magnitude of magnetic field at the center of loop is, so you need to find out magnitude at the center of loop, okay, n-sided polygon, from n-sided polygon. Okay, very good question. Okay, so we'll find first the magnitude of magnetic field, okay, at the center of polygon by one segment of the polygon. Okay, so how we are going to do it? So we know angle subtended by one side to the center is, because total angle is 360, right? So since angle subtended by one side to the center of polygon, to the center of polygon is going to be total angle is 2 pi upon side r n. Okay, so here I will make the figure. Okay, so this is like this. This one, this is the center. this one, this is 90, this is 90, okay, and this is theta 1, this is theta 2 for one side, okay, one side of the polygon, okay. This distance is r from center to vertex of the polygon, okay, and this distance, suppose this we can say, let's say it's small r, okay. So from here, right, for segment 1, this is for segment 1, okay, so it's n-sided polygon, it is n-sided polygon, okay. Okay, so now we'll find for segment 1, for this one, right, this segment, P1 is going to be the magnitude of magnetic field at the center by one segment, okay. This is, we know the formula we write mu0 I upon 4 pi r, mu0 I upon 4 pi r sine theta 2 minus sine theta 1. This is the formula, guys, okay, you need to note down. This is the formula, okay, to find the magnitude. So B1 equal to mu0 I upon 4 pi r sine theta 2 minus sine theta 1. Okay, so here we can say this is r is going to be, this is r, so r sine theta, this is this, well, we can say this is alpha, okay, r sine alpha, okay, r is going to be r sine alpha, because this angle is alpha and this is the this radius is r, right. So r sine alpha, capital R sine alpha, r equal to, that is this one, okay, this distance, so from here to here, okay, this one is r sine alpha, and theta 1 is going to be, theta 1 from here we'll find out theta 1. First we'll find theta 2, okay, theta 2, this one theta 2, okay, theta 2 is going to be plus 90 minus theta, because it is in right hand side, right, this is 90, this is theta 2, this is alpha, 90 minus theta, and theta 1 in left hand side, this is going to be minus 90 minus theta in left hand side, okay. Well, now we'll put the value. So B1 is going to be, B1 is going to be, B1 is going to be mu0 I upon 4 pi, mu0 I upon 4 pi r, okay, 4 pi r means this one, right, pi r, this distance, guys, okay, not from the vertex distance, this distance, okay, from side to center, okay, not at vertex, this distance, this is r, and r value we have already found, this is r sine alpha, okay. So we'll put here r sine alpha, and then sine theta 2 is 90 minus alpha, 90 minus alpha here, 90 minus alpha, and this is, okay, minus sine theta 1 is minus 90 minus alpha, okay, minus 90 minus alpha, right, because here theta 1 is equal to minus 90 minus theta, right. We have done mistake here, this is alpha, okay, this is alpha and alpha, because 90 minus alpha, okay, this is 90 minus alpha, so this is going to be mu0 I upon 4 pi r sine alpha into, this is going to be sine cos alpha, right, sine 90 minus theta is cos alpha, plus this is sine minus theta is minus sine theta, okay, this is minus minus plus sine 90 minus theta is cos alpha, right. So we'll solve it. So this is going to be 2 cos alpha, and 2 will get cancelled with this 2 4, so this is going to be mu0 I upon 2 pi r, mu0 upon 2 pi r cos upon sine cot alpha. Okay, mu 0 upon mu 0 I upon 2 pi r cot alpha. Okay, now for n-sided polygon, for n-sided polygon, we know alpha is going to be, because it's n-sided polynomial, right? Polygon, right? So this is going to be pi by 2 minus pi by n, right? Because it's n-sided. Okay, how? I'll tell you this one, alpha here. So because it's n-sided, right? So here we know this is for n-sided, the angle subtended by one side is 2 pi upon n, right? This is 2 pi upon n for one side, right? So this is going to be like this. Just wait. So this is the one. Okay, now we put the value. So it is going to be b1 equal to, b1 is going to be mu 0 I for one sided, right? Mu 0 I upon 2 pi r 10. Why this will be cot, we'll put the value of alpha, right? This is pi by 2 minus pi by n, so 10, I'll write it. Okay, so this is going to be cot pi by 2 minus pi by n. This is the value of alpha, guys. Okay, so cot 90 minus alpha is cos alpha, right? So cot pi by 2 minus pi by n is cot, that is 10 pi by n, right? So b1 is going to be mu 0 I upon 2 pi r 10 pi by n. Okay, so now this is for one sided, right? So for n sided, for one side of polygon, thus the magnetic field due to n side polygon is going to be, therefore magnetic field due to n sided polygon B is going to be n sided, right? n b1, because one side, for one sided is this, right? So this is going to be mu 0 I upon 2 pi r, and mu 0 I upon 2 pi r 10 pi by n. Okay, so this is the answer. Which option is matching? D, mu 0 ni upon 2 pi r 10 pi by n. Okay, option D is the correct option. Option D. Okay, guys. So, well, I'll stop here, guys, and thank you so much for watching my lecture. And I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my classes, which are absolutely free of charges and are going to help you to crack the exams related to physical science. Okay, guys, thank you. Bye now.